Chemistry is performed on the scale of atoms and molecules, but normally we can't see the atoms directly in order to identify them, to count them, or to watch how they interact with each other. Fortunately, each element has a characteristic mass that has been measured to a high accuracy and precision, so measuring the mass of a substance helps us to determine something about its atomic structure. That's why molar mass is such a critical value. It allowed us to know things about the atomic makeup of the molecules even before we could confirm that atoms truly existed. Although it might not look like it at first, calculating the number of atoms or molecules from a substance's mass is actually a unit conversion problem. First, we use the molar mass to convert between mass and the number of moles. Then we use Avogadro's number to convert from the number of moles into the number of atoms or molecules. To demonstrate, let's try to determine the number of atoms in 10.0 grams of water. To calculate the number of hydrogen atoms and oxygen atoms in 10.0 grams of water, first we're going to need the molar mass of water. So to find that, we're going to use the molar mass of hydrogen and the molar mass of oxygen atoms. We also have to know how many of each are in water. So water, hopefully we see by now, is H2O. So that's to say 2 hydrogen atoms, or 2 times 1.008 grams per mole, the atomic mass or the molar mass of water, and 1 times oxygen, which will just be 1 times the molar mass of oxygen, 15.999 grams per mole. Okay, and because these are the same units, we can just add them up. And what we find is that we have for water a molar mass of 18.015 grams per mole of H2O. Okay, so now to calculate the number of atoms from 10.0 grams of water, we'll start with what we know. So we're going to start with 10.0 grams of H2O. And now we want to start converting units from grams towards atoms. So the first step that we're going to take is to use this conversion factor, the molar mass that we just determined, and we want to cancel out the grams. So we'll make sure to put the grams on the bottom and mole on top. So now these will cancel. And for every mole of water, it's going to weigh 18.015 grams. And as we can see, we can just now take grams of water, and we're left with moles. So that's a good first step, but we're trying to get to atoms. So let's take it at least first to molecules of water. So to do this, we're going to use Avogadro's number, and that gives us the number of molecules per mole. And we're going to use the approximate value, 6.022 times 10 to the 23rd power. And this gives us a value of 3.3428 times 10 to the 23rd molecules, I'll just write molec to keep it short, of water. Okay, so now to get from molecules of water to atoms of hydrogen or atoms of oxygen, we need to know how many of each are in one molecule. So we've already said there's 2 atoms of hydrogen per molecule of water. So let's write this out first. So we start with 3.3428 times 10 to the 23 molecules of water. And the conversion factor we're going to use now is to say atoms of hydrogen per molecule of water. Again, we can see how this is just going to be another type of unit conversion problem. Okay, and there are 2 atoms of hydrogen per 1 molecule of water. So this gives us an answer of 6.6855 times 10 to the 23. And again, we can cancel out our units, some molecules of water, and we're left with atoms of hydrogen. And it's quite a lot simpler, but we can do the same thing for oxygen. Molecules of H2O. And there's one atom of oxygen per one molecule of water. So it's just going to be the same number. We're just multiplying by 1 in this case, so 3.3428 times 10 to the 23rd power atoms of oxygen. Okay, and for our final answer, we'll have to convert, not convert, but we'll have to put these into significant figures. So we can say 10.0 grams of H2O contains, so that's 3 significant figures, so we can have 3 significant figures, so that's 6.6, and we'll have to round up to 9 times 10 to the 23rd power atoms of hydrogen, and 3.34 times 10 to the 23rd atoms of oxygen. Okay, and again, we can throw a box around our final answers to make it easy for whoever is marking it or giving us feedback to see, and we're done.